Hello, everyone. I'm the magic paper talking.
Actually, steer this to the top of this and just decorate a little bit and actually settle in.
I hear someone's audio in the background. You might want to mute your speakers,
Fix the bookshelf and like actually make it nice.
unless you're talking to me, in which case you need to speak louder.
Organize all the closets and put the laundry away. Sounds good.
Oh, someone's got a crackling fire this evening. This morning.
I'm gonna get some snow.
Are we going to get it yet? Has any changes happened in the forecast? I haven't watched anything.
Yeah,
I've been
we're
putting out
gonna
fires.
get some. We're gonna get some snow.
Oh, good.
Yep, it's supposed to
Sort of.
start sometime around 2
Oh, really?
in the evening.
Let's see what's going on with us.
Okay.
Ooh, winter
It
weather.
says-
Sweet.
Yeah, it says we have bad weather till like next Tuesday.
Oh, that sucks.
At least.
Yeah, at least
That's
next
just the
Tuesday.
rain. At least this rain that's happening, and then
That means I got to keep my pool pump running. Dang it.
yeah.
This weather looks like it's going to be cold. Yes, Virginia Beach is having a winter weather advisory, as is Moyock, beautiful Moyock, North Carolina. And yeah, 70% chance of snow tomorrow.
Yep.
Starting
And
as early
then
as 2 a.m. Yep.
Tuesday, a chance of snow as well.
Awesome. This is going to be like snow day.
No, it's not. We're still gonna be
Except we
here.
have to work. It's snow day for grown-ups, so we can see what the parents felt like. What do you mean you're out of school? I gotta go to work.
Okay, we're still gonna have to go to school.
Hey, Peyton, is that a baby Yoda? Hey,
Thinking
Peyton, were
that
you
week
just holding up
is
a baby
over.
Yoda? Oh, I saw something. I thought it was a baby Yoda.
No, it wasn't. Might have been though.
I love my baby Yoda. I got like 4 or 5 of them around the house. Oh, I'm wearing my Pusheen kitty today too. Oh, excellent. I like your wanted baby Yoda poster. Yeah, I got my Pusheen cat shirt today. So I'm feeling my cat friends.
So many nerds.
Yes, we're cool folk here. We're proud of it.
No.
Okay, by the way, folks, this happened to me last night. I got a wild hair, decided to solve a problem and put it on my YouTube channel for all my physics classes. And I'm right in the middle. Like literally, I start it, and I'm 2 seconds in, and somebody goes, "Bing, bing, bing," like trying to get in. If it's not class time, don't come to my YouTube. Don't come to my Zoom meetings, unless I set up something for like an office, which I often do, by the way. So if anybody needs any extra time, we can set that up, and then I let everybody know. Unless it's something private, then it's just me and that one person. But if they don't tell me it's private, then I'll try to set up it for everybody. So you should know if you're paying attention to your email, you should know whether I'm having a meeting. So anyways, yeah, just if you see Zoom going at a random time that's not our time, don't click in. It like completely threw my groove off. Me and Stella.
You have a groove?
It's government process titanium right here. All
Get that
right.
replaced. Stay away from microwaves.
Yeah, exactly. Starts on the microwave, I start twitching and fall on the ground and pee on myself. All right. So yeah, that's Christmas Vacation. You guys got to watch that. That's one of my favorite movies that I watch 3 or 4 times every Christmas, along with A Christmas Story, and stuff like that. So, well, we're going to go ahead and knock out the very end of chapter 2. Did I do moon phases with you guys last time? I think I did, didn't I? No, I think I did that with 241.
Yes, you did do moon phases with us.
Oh yeah, but I got to the point where I predicted all of them, but I didn't do any of the particular exercises.
No, you
So
did no
let me make
exercise.
up a couple tricky exercises. I'm going to leave the reading of the eclipse stuff up to you. Just notice all the bold print terms are certainly fair game. This book doesn't talk as much in depth about the eclipses as their old textbook did. so it doesn't have the particular period at which the eclipses repeat themselves. But that's a neat, interesting fact. So you can do a Google search on that. But there's basically a period on which eclipse repeats itself, meaning the same day of the year, but it'll be shifted by like 8 hours. So it'll be 8 hours or later or something like that. But if you wait 3 times that Saron cycle, I think it's Saron. Might be getting mixed up with Fellowship of the Rings. Anyways, if you wait Saros cycle, if you wait 3 times that, then it'll actually put it, 3 times 8 is 24, and it gives you the actual same time at the same location. So you can actually see that eclipses actually repeat themselves. There's a lab that I'm probably going to get you guys to do this semester on eclipses, and you'll learn a little bit more about that. But right now, I wanted to remind you our moon phase diagram. We can use it to do some really cool things. So, for instance, let's say I'm going to write this as I go, and it's probably going to turn out really badly, but I'll try to write it as neatly as possible. So, Mr. Younger is returning from a date
Here he goes.
with his beautiful bride, Shawnee Bear. That's what she's known as in the Facebook community. And let's choose a very specific time. Let's say I'm kind of old, so I don't want to be, too terrible, but we'll say about 2:30 a.m. When he notices a fingernail clipping shaped moon low in the sky through his rearview mirror. One day I'm going to type these things up. Actually, they're all typed up. They're in your test bank. So Mr. Younger is returning from a date with his beautiful bride, Shawnee Bear, at 2:30 a.m. when he noticed a fingernail clipping shaped moon low in the sky through his rearview mirror. That means he's seeing a fingernail clipping, which, if you notice, when you clip a little bit of fingernail, the little piece that comes off looks like a little bit like a what type of moon? Anybody? Anybody? Like when you clip the end of your fingernail, that little piece pops off, and it's like a little thin sliver.
It would be waxing.
Crescent.
Crescent.
Yeah. It could be waxing or waning, depending on how it's oriented on the hopefully on the trash heap that you just threw it in, because you didn't just let it flick all over your house. But anyways, so question A: what phase is the moon in? I'm going to write an abbreviated question. What phase is the moon in? When did it rise? And actually, let's make this 3:30, not 2:30. Sorry about that. 3:30, not 2:30. When did it rise? When is the next full moon? And finally, D, which direction was he driving? Now, in reality, that 2:30 could have worked. It just would have taken a little bit more explanation. So I chose to do the 3:30. So for starters, anybody have an idea? Well, I've given you the hint of fingernail clipping, and you guys figured that out, that should be referring to a crescent. If I say something like a nearly full moon, what I mean by that is it's gibbous. It doesn't mean that it's a day or two before full. It could be a day or two after full. Okay. The main thing is it looks mostly full. I just don't want to take the time to write looks mostly full. Everybody understand that? So those are a couple buzzwords you got to be prepared for. In this case, you've got crescent, right? And of course, there's two crescent moons. There's a waxing and a waning. What time does the waxing phase rise and set? Anyone?
9 a.m. and 9 p.m.
Yes, it rises at 9 a.m. and it sets at 9 p.m. So it wouldn't even be up at this time, would it? So we know it's not the waxing crescent. Now we got to make sure Mr. Younger's not a crackhead, because I might have actually made the mistake of just making up a moon phase that's not possible. So we're going to double check and make sure that the waxing crescent, or excuse me, the waning crescent is in fact up at this time. What time does the waning crescent rise?
3 a.m.
Yeah, it rises at 3 a.m. And you see now why I chose 3:30 instead of 2:30. Remember, the fact of the matter is that the day before that midday, which is the midday, the day number 17 is the day we're actually calculating the waning crescent for, or excuse me, in the case of what we did, it's actually the day 24. But the day 23 was also a case. The day 22 was also a case. So it could have been as early as 2:30. That wouldn't have been a major deal breaker. Okay. But to get rid of that disparity, I just went ahead and changed it to 3:30. So we do see, in fact, that it's a waning crescent. Now, the waning crescent, we said it rises at what time?
3.
Yeah. So that also explains the fact that it's low in the sky, because it just rose. The way I treat it is basically the first 3 hours after it rises, it'll be low in the sky. The last 3 hours before it sets, it'll be low in the sky. And the middle 6 is sort of high in the sky. So keep that in mind. So for instance, for a waning crescent, it would be high in the sky from 3 a.m. Low in the sky from 3 a.m. to midnight. And then it'd be high in the sky from midnight, midnight until 6 a.m. And then it'd be low in the sky from 6 a.m. To 3 p.m. I know I screwed up. So the first 3 hours, 3 a.m. and then it'd be 4 a.m., 5 a.m. So it's 3 a.m. to 6 a.m. It'll be low in the sky. I flipped on the other side of the clock like an idiot. So from 3 a.m. to 6 a.m. it'll be low in the sky. From 6 a.m. to noon it'll be high in the sky, and then from noon to 3 p.m. it'll actually be low in the sky again. So everybody see how I'm doing what I call low in the sky and high in the sky. And like most things, it definitely rises in the eastern half of the sky and sets in the western half of the sky. And it's fairly close to the ecliptic plane. It's off by about 5 degrees. So that means it rises pretty close to east and sets pretty close to west. So we can sort of go on the assumption that it approximately rises in the east and approximately rises in the west. You might be off about 15 degrees or so by doing that, though. Okay. So when is the next full moon? Anybody have an idea how you might do that? Do we know the number of days from waxing crescent to, say, first quarter, third quarter, new moon, or anything like that? So from, I might have said waxing just now. From waning crescent, the way we chose it is it's 3 days before the new moon. But in fact, it only has to be 1 day to 6 days. It can't be more than 6 days, nor can it be less than 1 day, because that would actually put it on the day of new moon. So we'll just go on average and say it's 3 days. And then the time period from new moon to full moon is 2 weeks. So we're going to say approximately 17 days. Okay, but I would really accept any answer from 15 to 20. Everybody get how I did that? I'm doing this without a diagram in front of my face. I'm just remembering it, my pattern that I found, and I don't have to use the diagram anymore. You guys might want to create the diagram 2 or 3 times. That's normally what I do as one lab assignment, is I get you guys to answer some questions and then create that diagram and then fill it all out, like without looking it up. I mean, create it from your own understanding of how it works, knowing that, for instance, the moon orbits counterclockwise as the Earth rotates counterclockwise, and as the Earth revolves counterclockwise. So draw that and then put the sun on one side, blah, blah, blah. So that's something you should do. If you do it, like I said, if you do that 1 or 2 times, you will have discovered more than likely some kind of pattern that keeps you from having to do it every time. Now, here's the weird part. In which direction was he driving? Anybody have an idea other than Autumn?
Oh, shut up.
Anybody have an idea of how we might do that?
West.
Okay, so you're thinking west, and that's actually probably right on the money, because the moon
Right.
is just after rising, so it was rising in the east. And that means, since I saw it out my rearview mirror, what I would normally do if it's more complicated, I would draw a vehicle, and then I'd say, okay, well, the crescent moon was behind the car. There's the windshield and the steering wheel. Evidently, I'm driving a Corvair, ugly car, excuse me. And since it's rising, that must be the east, which means north is this way, which means west is this way, which means south is this way. So yes, we must in fact be driving west. Good job. So isn't that kind of neat? The practice tests are actually posted now, so you can start to get some feel for that. And yeah, I did. I was making sure I correlated it to the right book, because some time ago we switched, and I still got a lot of questions that I used from older books. So anyways, I just want to make sure I did that. So does everybody understand the process there? You're first going to be told some kind of detail about the moon, whether it's high in the sky, low in the sky, what time of day, or something like that. And it might even tell you something helpful like fingernail clipping shape, or slightly more than half illuminated, or slightly less than full illuminated, or just a little bit less than full moon, stuff like that. Okay. Or almost full moon. So watch out. That word almost might have a time component that, it is sometimes construed to have a time component. I am not, if I use the word almost regarding almost full, I am not referring to time. It could very well be a waxing or a waning gibbous. Once you get what the phase is, then you can go with your model and just say what time it rose. In reality, we know, for instance, that a waning crescent is what happens after a third quarter. And we know a third quarter actually rises at midnight and sets at noon. So long as it's rising after midnight, then technically it's still a waning crescent. So that's why it gives me wiggle room. Like I could have wrote 2:30 there and left it. But like I said, we always stick to 3 days later, and that makes it a little easier. Then you also have to know, how long is the lunar cycle? And obviously it's technically wrong, the model we made, because we said the lunar cycle is only 28 days. And we said that because it's so easy to work with a quarter being 7. So we're definitely going to be off by a couple days if we use this, to predict months in advance. At least 2 or 3 months in advance is going to be potentially off, but you can still get amazingly close. So if you pulled open, say, my moon app right now, which is what I'm going to do, I got to actually pay for it again. Just discovered, because they've made it where I can't change the date. Today's date is not December 15th. So I got to go to now. Today is that day. All right. So evidently being a pain in my rear again. Okay, now let's see if I can see. I think today, yeah, today's pretty close to a full moon. In fact, it looks like today it's 98.8% full. The actual full moon, on the other hand, if I go back to the calendar, the actual full moon occurs at 2:12 p.m. on January 28th. So that's the instant that the center of the moon, the center of the earth, and the center of the sun all were in one plane. Not necessarily one line. If it was one line, we'd get an eclipse. Okay, so you can read from the rest of your chapter 3 material. You can read things like about penumbra and umbra. The umbra being the shadow cast by a body, the darkest part that no light from the, for instance, sun can get to, and the penumbra is right next to the umbra. Pen means just before, or, for instance, it's often used the term penultimate, which means next to the last. So you can also use the prefix pen to suggest next to. So that's some of the things you'll learn about in this. But the main thing is, because the Earth and Moon the ecliptic and the Moon are not in the same plane exactly. We're lucky in some sense because we don't have a new moon and a full moon we don't have an eclipse every new moon and full moon. Otherwise, if they were all in the same plane, then when the moon comes between the earth and the sun, then it would always block out the sun, at least for, however long it takes. And your book talks about that. So you can be prepared to memorize those things at least long enough for this first test. But because it's tilted at like 5.5 degrees, a lot of time it goes over top of the sun, and other times it goes below the sun. Okay. And then the same thing happens when it gets on the full moon side. The full moon is the side where you could potentially have a lunar eclipse, because then the shadow of the earth is landing on the actual moon. But again, the moon could pass over that shadow or below that shadow because the tilt of the two axes. But it turns out the axial tilt is, set like, here's the Earth's rotation axis, and here's the ecliptic, and then here's the moon's tilt. That's axis tilt's like 5.2 degrees or something like that, and it sets at a little angle, and that basically stays set. So it goes around like this all year, but it's not exactly set. It's still processing a little bit. So basically, there's a time in our Earth's orbit where it's in the same plane as the Earth Moon system, as the Earth Sun system, and that's called one of the nodal points. And it lasts long enough, around 30 days, so that you could possibly get a lunar and a solar eclipse in the same month. But when you're outside of that, it's no longer eclipse season, because the tilt is not such that the plane has a line across it and that the moon and sun are in. So when you go to the other side of the year, you have another one. So when you go to the other side of the orbit, on the other side of the sun, you're going to have another type location. And you can see that diagram on page 50 of your textbook. So it's basically called the line of nodes. And whenever that line of nodes does happen to include the sun and the earth, or sun and the earth and the moon, then you're going to get an eclipse no matter what. And it's just a matter of, if it's a full moon, it's going to be a lunar eclipse. If it's a new moon, it's going to be a solar eclipse. Okay. And like I said, we'll do a lab later on. It'll get you a lot more familiar with eclipses in general, and you'll be able to make predictions, and even, just tracking the last several moons, you could predict when the next eclipse would come if you really wanted. So it's kind of, or not the next several moons, but the past several eclipses, and you can use that to give a rough estimate around when the next one will come. The problem is, like I said, those planes in your book, it's showing them on this side and this side of the orbit, where the nodes points away from the sun, because the sun's over here. So right here is when that nodal line points towards the sun, and right over here is where the nodal line points towards the sun. So those are eclipse seasons on either side of the moon. I said the moon, on either side of the sun. But that position, that angle or whatever, changes a little bit each year. So the eclipse season changes by a couple of days every year. So that's what gives us that bigger cycle that we were telling you about as well. So anyways, I will leave chapter 2 alone now. We have essentially covered everything. It does give you some predictions of eclipses to come. For instance, in America, we've got one April 8th, 2024. That will actually go. That's. I don't think Virginia is going to get to see that one. August 21, 2017. We did see that one. I actually hosted some things at our observatory for that. But you can fly to other places or be located at other places and catch the eclipses as well. A lot of people do that. They we call them rich people, or at least people willing to sacrifice a lot to save up money to go to these trips. But that's kind of cool. We can predict that with that Heavens Above website that I showed you. And you can predict it with the Starry Night software, the Sky software, Stellarium software, Redshift software. All those software packages can easily predict when eclipses occur. So what we're talking about now is the motion of astronomical bodies. And we've sort of gotten that already. We've already talked about which direction stars move at a given time of day or whatever. Like if I say a star is due east of us at 7 p.m., you all know at 8 p.m. the star will have moved which direction or directions? Anyone? So let's switch to my document cam, refresh our memories. The diagram that you should know, of course, came from the celestial sphere model, and it just came from me standing on top of that Earth in the celestial sphere. And watch this. Hold on. Damn, I always turn the video off. Miss the arrow. So imagine me on top of the Earth, standing right here. Celestial spheres up above me. This is, say, due north, and the celestial North Pole is at the end of that pin. So I'm going to stand up here and stick my arm up and touch just above the pin where the pin touches the celestial sphere. In other words, it'll be just above Polaris. And then you realize the celestial sphere is rotating this way. So if I looked at it, I would see, things around the North Star are rotating in a counterclockwise direction. So that was what allowed me to make this diagram, which you've seen hopefully numerous times now. North is in the center of the horizon that I'm dealing with. So I draw a little dotted line up, and for our locations, 37 degrees north, Polaris should be about 37 degrees high. Okay, that's supposed to be a vertical line. I don't know why I went curvy like that. Anyways, now I'll make a series of concentric counterclockwise circles, with that being roughly the center. Obviously, I missed a little bit, but that's okay. Continue to make concentric circles. And then I remember east is over here. North is there. West is there. So once you confine them as counterclockwise, then your little arrows have to be this way, this way, this way, this way. And your arrows over here have to be this way, this way, this way, this way, this way. And of course, you can put them up here as well to help you. So if I saw a star directly east of us at 7 p.m., I expect it to move up and to the right. The answers are always up, down, left, right, up and to the left, up and to the right, down to the left, down to the right. So that's what we get to see when I look north. Of course, we also had the other diagram when we look south. It's a lot simpler to draw. It basically has an arc whose center is below the horizon and is directly below due south. So this is our highest point, and it's going this way. And of course, this is the east side, and this is the west side. So if I see a star directly south of us, I know it's at its highest point that it'll ever be. And if I wait an hour later, it'll move down and to the right, just like west. And then, of course, I told you can also do a star to the right of Polaris or above Polaris or to the left of Polaris or below Polaris. All of those, you can get the answers to these from. Okay. So that's one thing we see day in and day out. The constellations basically have the same shape they did thousands of years ago, though we've been able to track that they move a little bit. So we know they actually moved somewhat and changed a little bit, but literally over thousands of years, the diagrams are very close to being what they are today. For instance, Gemini still looks like, basically the idea of the two twins. So with that in mind, we can say, well, I know how things move. Things rise in the eastern half of the sky and they set in the western half of the sky. And if my right ascension, or excuse me, if the declination of a particular object in the sky is higher than my latitude, then I know it's going to never go into the southern half of the sky. It's always going to stay in the northern half. And if it's less than 37 away from the pole star, the North Celestial Pole, so if it's 90 minus 37 or less, then all those stars will never set at all because they're going to constantly be above the horizon. So we know how stars are going to move. If we look to those ones that are less than 37 degrees from the pole, then I know they're circumpolar stars and they're never going to set. And they're going to move in a counterclockwise circle at a rate of about 360 degrees every 24 hours, or basically 15 degrees per hour. If I look to something that's a little further farther from the North Celestial Pole, let's say not quite as low as 37 degrees declination, then those stars will come up and reach their highest point actually due north of us. Right at 37 degrees, if we are exactly at 37 degrees latitude, right at 37 degrees, that star will rise north of east and will actually hit directly above our head at its highest point. It'll be at our zenith, and then it'll set again north of west. From there on, all those other stars are going to be doing this stuff. They're going to rise in the east, reach their highest point due south, and set in the west. Okay, and when I say east, I mean the east half. And, you know, its declination is going to tell you how far to the south or to the north of due east it's going to rise, and how far to the north and south of due west it's going to set. Okay, so that gives us just an idea of how the things move in the heavens. And you can see, because the celestial sphere is still useful, you can see that clearly that is fairly accurate, because if it wasn't, we wouldn't still be using it. Now, the other thing we had was we had these other things called planetos, which you've seen from the video, means wanderer. That's what Greek planetos means. And they had the planetos, which would come and wander through a constellation. So, for instance, you might have a pretty little constellation like this. And another one right here, here, and here. Okay. This constellation, by the way, those two are the brightest ones. This is supposed to be, anybody guess it? I use it almost all the time. Is Gemini. It's Gemini, right? So that's the constellation Gemini. So what the ancients noticed is these wanderers, every now and then, what they do is you'd see this two stars, for instance, rise in the east first, and then it would move off like this, and then set in the west. And these two stars, since they came up first, they'll be ones to go down first, and they would always look like that. But normally what you would see is the wanderers would just come through like this. Like if I took an observation of them every 3 weeks and plotted them versus that constellation, they're still doing the same thing every day. They're still rising in the east. So one day they'll be here and they'll be there that whole day. They're barely moving on a daily standard. And if you come back and look at that same spot tomorrow, that same spot right there tomorrow, you'd see that they're still pretty much in the same spot. Okay. That's normal everyday motion. That's called prograde. And it's basically faster than the stars. And we now know it's faster than the background stars because the planets are closer to us than the other stars. That is called, like I said, prograde motion. And that's normally how things work. You can even look at it, for instance, if you drew a real model of the solar system, not the Ptolemaic one, but a real model of the solar system, we would have the sun in the center, right? And then we'd have Mercury orbiting closest. So I'll just put an ME for that one. We have Venus ordering second closest. And we'd have Earth orbiting third. And then really the only ones you can see are Mars, Jupiter, and Saturn. And that's roughly what they look like. They really do look more circular than they look elliptical, even though my drawing looks like potatoes. Okay. But normally what happens is you've got a small period of time where Mercury and Venus will be really on the same side as the Earth. Most of the time they spend, remember, if they're on the same side of the Earth, it's only like, this little part of their orbit right here. So some of the times what we see is they're in front of the moon, and notice, or excuse me, in front of the sun. Everything is rotating on this diagram, is revolving counterclockwise. So what you normally see is either the Mercury being here or here. Both of them look the same to us. They're just to the left of the sun. And in this case, Mercury would be getting farther and farther away from the sun. But in this case, it'd be getting closer and closer to the sun. So they don't act like this that much. It's not really easy to say it as prograde, retrograde. So what we know is we realize if it gets closer and closer each day to the sun, then it must be on the, like at this location. But if it's to the other side of the sun and it gets farther and farther, then it's at this location. If it's at this location, though, then it'll get closer and closer to the sun every day. And that's the way Mercury and Venus both behave. They're the inner planets, the ones that are closer to the sun than us. Now, as you can tell, most of the time what you see happening is Earth moving this way. The sun, which appears, we can pretend it's sitting still because we're saying the Earth is moving this way. And it really is with respect to this whole orbit system. But if you take, for instance, Mars, we'd see Mars moving this way. Our Earth, by the way, is also rotating this way and revolving this way. This arrow shows right here. Okay, so it's revolving this way and it's rotating this way. So what we're seeing is basically the stars as if they're moving this way, from here down, because the Earth is rotating this way. So you can see that's why this planet appears to be moving faster than the stars, because the stars are actually going a little bit this way. But it continues on, continues on, continues on, continues on, continues on, continues on. Then when it starts to get around here, something weird starts to happen, because now this thing's going faster than us. And you can see it actually, the Earth, which is rotating this way, sees this thing moving faster that way as well. And what happens in that scenario is, let's say we have another constellation. Let's say we have the constellation Cancer. So Cancer to me looks a little bit like this. Okay. And what we might see is a planet, for instance, Mars, and it'll come through. And this again is like on 3-week intervals. It's just doing its thing. And then every now and then it'll start to get a little brighter and real bright, and then start to get less bright again. And it'll finish its path out like this. So what happened is it went prograde, 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 prograde. And then it started going prograde, 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 prograde again. This little part of the motion right here, though, was called retrograde, meaning it was going the opposite direction. And we know what's happening. What's happening there is Mars is actually catching up and passing us. Okay, so when we're on this side with the moon or with Mars, then Mars is going to go faster than us, and we can sort of make use of it this way. What I want you to think about in this model, this is the reality of the situation. This is Earth moving along. So we're going to represent Earth as a UPS truck. And the reason why I use a UPS truck is a UPS truck has this cool little driver's seat that you can just pull up a little lever and it'll turn and face sideways, right? So instead of driving like this, you could turn like this. So what I'm going to do is I'm going to imagine myself being a UPS driver and representing planet Earth because, I'm spherical. And I'll be driving in the fast lane, right? And let's say I'm driving 65 in the fast lane. So, I'm not, dilly-dallying, if you will. It's a 60-mile-per-hour speed limit, or say a 55-mile-per-hour speed limit. I'm doing about 65. Well, there's somebody that wants to pass me and they're going like 70. Okay. If they're going 70, they're going to pass me, right? And I'm staying in the fast lane because I'm really doing 10 miles per hour over speed limit. That's plenty. So what I see from me sitting standard sideways position instead of the normal standard driving position is I see, and don't do this, it could be dangerous. I'm a professional. So I see this fast car go from my right to my left and goes on past me. That's like normal everyday motion. But watch what happens when we take a hard left turn. So if we take a hard left turn, I'm in the inside lane. And because I'm any of the ways, despite the fact that I'm going a little slower, being in the inside lane makes me appear to be going a little faster because I cover more degrees per second. So what I then see is the red car, which was going from my right to my left, all of a sudden slow down, comes to a stop, and then starts to go from my left to my right as I pass it. And as long as I'm in that inside lane, and that inside lane is a tight enough turn that I appear to be faster, that's going to continue going from left to right, left to right, left to right. And then we straighten back up, and reality sets back in that the red car is actually faster than me, so it starts going from right to left again. Okay, so that's what's happening normally. Normally, this is the red car in the diagram. See if I can do this without turning it off this time. So normally, the UPS truck is slower than Mars. So Mars goes from my right to my left all the way across here. That's normal motion. But then when it gets around here, I get to show off because I'm going to go a little bit faster, and that's going to cause the planet to go left to right instead of right to left. So that's really how we were able to explain it once the Copernican revolution came along. Okay, so there's a scientific revolution and a Copernican revolution in the way I like to teach it. In reality, it's sort of one big thing, and it happened at different places at different times. But basically, I separate them personally because the Copernican revolution had some profound effects. It took us, in the pre-Copernican model, which was the Ptolemaic or Aristotelian model, you basically had the Earth was the center of the universe. And then, like I said, Mercury and Venus, we had to explain their weird motion, so we had to put an epicycle on a deferent, this thing being the deferent, this thing being the epicycle, and we had to force the center of the Earth and the center of this epicycle to be on a line that was also on the center of this epicycle, which was for Venus. This one was for Mercury, and it had a deferent as well, right? So that was our system. And then outside of that, we had the sun. I skipped the moon. The moon would be in a small orbit around here, but we'd have the sun orbiting out here. And it didn't have an epicycle. It just had an orbit, so it would go this way. And then beyond that, I'd have Mars, Jupiter, Saturn, and that would be it. And in fact, if we discovered another planet, we'd have to watch it for 500 years under the Ptolemaic model just to make an estimate what the orbit's like. Whether we'd have epicycles and deferents and all that. And it got so bad that to correct for it, they also had to move the Earth off center, and they ended up making a equant point where if you were at the equant point, which say might be here, then all these velocities look like they're not changing, and the Earth wasn't there. So, all the stuff that Aristotle was teaching us, we had sort of gotten around by a little bit of trickery. Trickery was that this was a sphere and this was a sphere within a sphere. Right? So we kept the heavens spherical. And we even had to move the point because the things couldn't speed up or slow down because that was Aristotle's idea about the heavens. So we had to switch the point from which we would view just to make sure that all the things moved at a constant rate. So we were doing all this weird crap, and it just didn't work. So Copernicus comes along and says, hey, we've lost track of what Aristotle taught us. We've got circles on circles and equant points and all this. This is just, we've drifted too far to a field from Aristotle. So he said, let's put the sun at the center and just put everything in circular orbits, more or less like this. Okay, so this is actually circular orbits if it was drawn by something other than a moron. So with these circular orbits, he automatically got the idea that Mercury is fastest, has the least amount of time from one location to return to that location, just because it's closest to the sun. Venus was the second and had the second longest period. Earth was the third, Mars the fourth, Jupiter the fifth, and Saturn the sixth. And he was able to basically get fairly good results, just as good results as these were until a new paradigm of experimentation came along. Okay, so this Aristotelian model was being threatened by this one, But by this time, we'd had 1,000 years of, since Emperor Constantine introduced the Roman world to the Christian doctrine, we had priests, they, like Paul, for instance, was ultimately made the first pope of the Catholic Church, even though there was no such thing as a Catholic Church when Paul existed, So they made this, and these people had taken and read their scriptures, and they rated them very thoroughly. This isn't, like we skim our Bible or something like that. This is like reading it, memorizing it, studying it, all that stuff. And they had made all this work with the Aristotelian thought. And it made perfect sense that if hell's going to be this horrible place, it should be at the center of the earth. And if the earth is not the center, then that's kind of weird. So that would screw up everything. Not only that little scenario, but just to give you that as one particular process. But we didn't have any real good experimental evidence that suggested this was absolutely better than that. It was easier, and initially the Catholic Church with the Copernican model was completely excited because they could pay their astrologers cheaper. Right? Astrologers don't have to do as much work if you just make the circular orbit. And remember, their job was to predict where the planets would be in what constellation at various months for the next 10 to 20 years. They would make an almanac, and that almanac you could look up as a leader and decide whether your horoscope was in favor of you going to war or marrying a wife or whatever. So all that stuff was cooked in together. If you're doing it with this, you've got to recalculate the size of the epicycle, the rate at which you go around the epicycle, the rate at which the epicycle goes around the deferent, at least on these outer planets. All that stuff's got to be tweaked and tweaked and tweaked to fit the most recent data. And then you go back and analyze it so you can figure out, okay, when is Mars going to be in the president's constellation? Okay. So that was a lot more complicated than this. So astrologers and astronomers, which there was no difference back then, and they didn't even use the word astronomy, but astrologers were happy with it, as was the church initially. But Copernicus was also smart enough to not publish it until he was on his deathbed. A guy by the name of Radicus talked him into it, and he went and published it and got literally the first copy of it on the day he died. So it was really a smart move by him. But no one had any problems with it. And then this guy comes along by the name of Tycho Brahe, and Tycho Brahe is he really is a brilliant experimentalist. He's nobility. He's got a lot of nobles that like him. He will do cool things and then name it after these noble people. And when he does so, obviously that puts them in his favor, and they will give him money. In fact, he was given an island off the coast of Denmark called Haven, but they're probably consonantal words, so they're really hard to pronounce. But Brahe, Brahe, is his name. And when he comes on the scene, he doesn't have a telescope yet. He just has basically a giant protractor, if you will. So he has this giant protractor mounted like on a wall. And I say giant, I mean like it's 0 to 90 degrees, right? And it's maybe 6 feet tall. So you can split the degrees down very fine to even on the order of 10 minutes of arc and stuff like that easily, right? And he has a hole in the opposite side of the room he's built, and he basically takes the taxes that he gets from the people. And he was not a nice landlord. He kicked people out in the middle of the winter. It doesn't matter that you're up in Denmark and it's freaking cold. He kicked you out when you missed, because that was his experimental money. And he was a good mathematician. He thought he was better than he was. In fact, he's this weird character in history. He's sort of, I call him like the Russell Brand of the time. So Russell Brand, y'all know him. Get him to the Greek and Forgetting Sarah Marshall. Those movies. He was married to Katy Perry. So that's Russell Brand. He's sort of the image of a party animal, right? And that's what Brahe is. Brahe's super wealthy. He has parties all day and all night. He's nobility, so he has a ton of people over. He's got this cool castle. One night he gets a friggin' deer or elk drunk, and it falls down the steps and dies. It's horrible. He's got a pet human, which we now would call like a little person, or a person of small stature, dwarf or something like that. He has one of those as literally as like a pet. So he's not, from our standards of niceness, he sort of sucked a lot. Okay. But he did have these cool parties all the time, and I say cool, but they were also bad things. But he was known to sit there and get drunk all day, drink alcohol all day, and eat big hunks of deer hide and meat and all sorts of stuff, just eating, and then stay up all night studying and measuring the stars. And he had this cool model that he thought could bridge the gap between the Copernican model and the Ptolemaic model, only he wasn't quite the mathematician he thought he was, so he couldn't get it to work. So here's his model, and thank God it was lost to the dustbin of history, but here it is. His idea was this. So we have the sun right here, okay? And the Earth is, in fact, going to orbit it. So the Earth right here is going to orbit the sun, just like we think it does. Here's the weird part. The moon, this isn't the weird part, the moon is going to orbit the Earth. And in fact, Mars is going to orbit the Earth. Venus is going to orbit the Earth. I don't know. I'll put Mars first. I should have put Venus and then Mars. So.
Do you know how far the Earth would have to be out there for all those planets to circulate through it?
Yeah. It's not a pretty model, but it gets rid of a lot of the current concerns. As you'll see, the final nail in the coffin is not really a nail in the coffin if you're using the Brahe model. So this is the crazy Brahe model. Yes, of course the Earth orbits the sun, but everything orbits the Earth. So that's kind of the crazy Brahe model. Well, that gives us a time to introduce a guy by the name of Kepler. And Johannes Kepler was he's sort of the Mike Pence of the astronomy world. So you know how Mike Pence is seen as very straight-laced, probably praised 12 times a day, and I mean these as complimentary things, and I mean them as complimentary things for Kepler as well. But Kepler had a problem. He was a brilliant mathematician, and he was really good at astronomy and wanted to be an astronomer, but he had horrible eyesight. I think he had rickets and shingles and all sorts of weird diseases. His mom kept getting arrested because she's an old lady with no teeth. An old lady with no teeth creep out old men, and old men have power, so they arrest her as a witch. And he has to go down and act as a lawyer for her and get her out of jail. I mean, literally had multiple times he had to go get his mother out of jail for being a witch. She wasn't doing anything weird. She just, that was a typical thing to happen to spinsters, if you will, or people that were married and just were widows now. They would often be accused of being witches. It was a terrible time to be alive in many ways. So that was sort of the life backstory of Kepler. And one day, he's sort of like me. He's not that great of a teacher because he lets a lot of things catch his mind and then he goes off on tangents, not unlike what I'm doing now. So one day he's sitting in his class that he's teaching. And this is like kids from 5 and 6 years old on up to maybe 12. And he says he's drawing out the planets in the Copernican model like he's trying to teach his students. And then he realizes the number of heavenly bodies is exactly the right number for them each to be separated by the perfect solids of nature. So he starts literally on the sidebar, doing the calculations while his class, who's paying him to teach, is going crazy out of boredness. So obviously that job wasn't the best job for him. But in the meantime, he works out this model and he spends years working on it. And he's got this really great idea that this has got to be it. God speaks in math. I mean, that's the kind of person that Kepler was. It was all about God, and God was trying to communicate with us through the heavens. And, he worshiped the sun. He did a lot of weird different things that wouldn't be taken normally nowadays. But he wrote a little paper on this model and sent it out to all these people, one of which was Brahe. And Brahe says, wow, this man's a really good mathematician. I could use him. So he offers him a job. So now you got Russell Brand running a castle with Mike Pence being his mathematician in charge. And you can imagine that didn't go well. And it's probably not unlike, I don't think, Trump was like that. I mean, I'm sure he didn't throw parties and stuff in the White House, but still they were quite different characters, just like Brahe and Kepler were. But it was kind of a sad thing because Brahe was really a brilliant scientist, and Kepler really respected him for his science. I mean, he even dedicated his book to him, which was a book where he basically revolutionized the world. He dedicated that to Brahe. But what happened was he had gotten there, and Brahe wasn't giving him the data because Brahe realized he was really brilliant and was going to steal his thunder. So he tried to give him data a little bit at a time. And it was really frustrating to Kepler, who saw this guy as a lazy slob in terms of partying all day, and then putting in a few hours of work and then sleeping until midday, and then starting to party over again, and then do some work, drunk, and so on and so forth. But still, he knew his data was good. He knew his science was really good. Brahe had done things like shown that a comet was actually closer to us than the Earth was to the sun. That's a big deal because remember the Aristotelian model says that the heavens are are not non-changeable. So a comet coming in closer than the Earth, meaning or even closer than the Moon in that case, would suggest that the heavens did change. So that's one of the things he did. He did a lot of stuff. He located a guest star, which was a nova. That we know exactly which one it is. He located that and was able to use parallax to measure how far away it was. Some really big stuff, especially for someone without a telescope. But in all this, Kepler gets tied up, and one day Brahe's having a party, and I don't know if you know this, but nobility, they don't pee and poop. So that's what happened with Brahe is he didn't pee or poop the whole day he was partying. His bladder burst, he became septic, and he died. A horrible, painful death. Not unlike the death of George Washington, who also died of a burst bladder. So it was a terrible, terrible death. And then of course, there was a legal battle. Like, where's all this stuff go? He didn't have any kids. What are you going to leave it to? And his family was rightfully trying to protect his place in history by not just handing over the stuff to Kepler, who would actually get all the credit. And that is what ultimately happened. So they were right. I mean, a lot more people have heard of Kepler than have heard of Brahe. But still, he ultimately won the battle. There was actually stories that he had stole it in the night, like Kepler broke into the lab in the night and stole the books. I haven't found that historically backed up, but historically we do know that ultimately he won the right to use the data. He worked through, first thing he tried was the Copernican model. That didn't work. It was in fact just as bad off as we thought as the Ptolemaic model. He then tried his own model, and like a good scientist, when he saw it didn't work, despite the fact that he spent years working on it and doing all the math, he threw that model to the side and said, well, that's not one. So he had to start over anew, and he really depended on his faith of Brahe being a brilliant astronomer, because there was one small difference in his data that no one had caught before, and that was ultimately the thing that made him throw all those other models out, and he ultimately came up with Kepler's 3 laws of planetary motion. I will say them out loud. They're written in your book. I don't want to take time to give you time to write them, but the first law is that the sun is at one focus of an ellipse, and the planet orbits the sun in ellipses. So all the planets orbit the sun in ellipses with the sun at one foci. Well, what is that? That's the first law. All the planets orbit the sun in elliptical orbits with the sun at one focus. So what does that mean? Well, an ellipse is like a circle with 2 centers. That's one way of thinking about it. So if I turn back to my document cam, if I took a nail and stuck it in plywood right here, say, and then I took another nail and stuck it in plywood right here, say, and then I attached a string to this one, tying a knot, and made sure the string was quite a bit longer than the distance between them. And I tied this one here, and then I stuck my pin in it to hold it tight. If I trace that path out, it would make that shape, an ellipse. This long axis, which is supposed to be symmetric, like the bottom half is supposed to be a mirror image of the top half, that long line is called the major axis. And this short line right between the two is called the minor axis. And if you wanted to talk about half of them, like from here to here, that's the semi-minor axis. Or excuse me, semi-major. So this is semi-major. And this is semi-minor, okay? And the flatness, the more elliptical it looks as opposed to more round. So you could have an ellipse that had the 2 focal points, the 2 nails really close together. That has an eccentricity closer to 0. So E is very close to 0 here. This E is closer to 1, where 1 would be, you keep getting narrower and narrower and narrower until it goes to a straight line. That's when the elliptical, the eccentricity is equal to 1. So this might be, say, 0.7. is on the order of E. So that's what an ellipse is. The focal points would be these 2 nails, and there's nothing special at the other one, but the sun's going to be at one of them. So that's his first law. That already has Copernicus rolling over in his grave, because the ellipse is a bastardized version of the circle. And the circle, of course, is just a slice of a sphere, and the sphere really is the heavenly shape. So that would have driven Copernicus crazy. And it's really amazing that Kepler was able to figure this out, because it turns out the eccentricities of these are so much closer to 0 than they are to 1, that if you laid the orbit of, let's say, Mars right next to the an actual circle of the same size, you couldn't tell which one was the circle and which one was the ellipse unless you started doing some measurements. That's how close to circles they are. So it's really impressive that he was able to work out that math in such a way that he discovered the planet was orbiting in exactly ellipses, not ovals, which are less well defined, but specifically ellipses. So his first law was elliptical orbits with the sun at one focal point. His second law said they swept out equal areas in equal time. So if I draw that ellipse again, and let's imagine the sun right here, if it takes 30 days for a planet to go from here to here, imagine that as a pizza slice. Okay, from here to here is 30 days. Now, if you go out here, if you want to find another 30-day interval starting, say, here, you have to make sure you have the same amount of pizza the same amount of cheese on this slice of pizza as you did on that slice of pizza. Well, this slice of pizza is a lot longer than that slice of pizza, so you'd have to make it a lot narrower. So maybe this would be 30 days way out here. That's what Kepler's second law says. It says the planets orbit in elliptical orbits, being the first law, with the sun at one focal point. And the second law says that they sweep out equal areas in equal time. So that tells you, hey, when the planet is closest to the sun, it's going to go faster, because it's going to go all this distance in 30 days, whereas when it's way out here, it's only going to go this distance in 30 days. So that's the second law. That's his second law. And then finally, what he did was he did the rudiments of science. And the rudiments of science, when you're first discovering some things, like maybe you discover the idea of a calorie, and you understand that your body is burning calories, and you do a plot of calories eaten down here versus your weight. Now, your first idea is, I wonder if calories eaten is directly related to my weight, thumbs up, or if it's inversely related, meaning the more calories I take in, the less I weigh. It's a very simplistic model, but that's the rudiments of science. I'm starting to incorporate some quantitative aspect of it. If one goes up, does the other one go up too? And if one goes up, does the other one go down? So if you made a plot of that, like for this, you might see that, in fact, as the calories go up, the weight goes up too. That is a thumbs up relationship, because as this one went up, which is to the right, this one went up, which is to the upward direction. Okay. But it's not a straight line, so I can't just write out an equation unless I do some fancy mathematics. So then you try weight to the first power and calories to the second power, or weight to the first power and calories to the third power, or weight to the first power and calories to the 1/2 power, or to the 1.5 power, so on and so forth. You keep doing this over and over and over, and then you start leaving this one alone and start changing that one, and then you start to where you have to actually change both of them. And you keep doing that over and over and over again. And what he ultimately found was, when he compared the period of the orbit to the semi-major axis of the orbit, it made a curve like that, meaning the larger semi-major axis had the larger period. But when he plotted t squared and a cubed, it made a straight line. So Mercury was here, Venus was here, Earth was here, Mars was here, Jupiter, Saturn, all of them right along a straight line. So at that point, he knew t squared is equal to, if you use the right units, which are years and astronomical units, t squared is equal to a cubed. That is Kepler's third law. Okay, so we know how many years does it take for the Earth to go from here to here?
1.
1. So 1 squared will be, of course, 1. How many astronomical units is the orbit of the Earth? You remember what the average radius of the Earth's orbit is? It was the very definition of the astronomical unit. So if we do that, if we take 1 cubed, because the Earth's semi-major axis, which the semi-major axis, remember, is this distance from here to here, that's also 1, and 1 cubed is 1. So clearly, yes, 1 square, or t squared is equal to a cubed in the special case of using years and astronomical units. Newton comes along, discovers the law of gravity, and puts a constant in there that gives you all the other parameters it depends on, one of which is the mass of the sun. Okay, and the other one's the gravitational constant. But if you're using units of astronomical units in years, then you can do this all day long. Now, the other neat thing is, notice when the, if this is the sun, this is the Earth at what we call perihelion, when it's at its closest. So it's only this far away. But when the sun is, or when the Earth is over here, it's at aphelion, when it's farthest away. So if you look and add the distance at aphelion, which is all this distance from here to here, everybody see that? This is the aphelion distance for the Earth, all the way to the focal point to this end. And this is the distance at the perihelion. If you add those two, we know that this half is just 1 AU. What's the total length across there? What's this distance plus this distance? Remember, 1 AU is from here to here. So can somebody tell me what this distance from here to here is plus this distance? I don't need to know one by itself. I just need to know what's the sum of these two. If I add this distance to this distance, what's the total distance?
Would be 2 AU.
Yes, it's 2 AU. Because it's 1 AU to here, it's 2 AU to here, because that's also an AU. So it doesn't matter that it didn't break them in half. The point is, from here to here plus here to here gives you 2 AU. So if you take the average distance, it'd be 2 AU divided by 2, which is 1 AU. So we will often disguise questions by saying the average radius, or the average radius of the orbit of the planet Chibubula, is 14.5 AU. How many years will it take it to orbit, assuming it orbits the sun? So all the things orbiting the sun obey this equation. If they're orbiting something other than the sun, there's going to be, you got to put that constant in there. So if something orbiting Jupiter or Earth, the idea works. It's still going to be t squared versus a cubed gives you a straight line, but it'll be entirely different slope for different objects being orbited. Okay. So that's Newton's third, Kepler's third law. And the way we implement that mathematically, I'm going to go ahead and show you, because this is one of the few calculations we do in the entire semester. So let's say we found a planet whose semi-major axis is 14.5 AU. Again, my question would be more worded a little more in camouflage, if you will. I would say we've recently discovered a planet that we've never seen before orbiting our sun, and it's called Jabubula. And its semi-major axis has been determined to be 14.5 AU. What is the period of its orbit? So t is equal to question mark. So this is how you do that math. We know that the equation is t squared is equal to a cubed. Okay, again, this is in years and this is in astronomical units. And it doesn't matter if you use capital or lowercase or whatever, just as long as you know what you're using. Okay. So in order to do this, I see I've got A, and evidently A needs to be cubed. So I will type on my calculator 14.5, push that in the button. So I just mark it as a button like that. And then your calculator will either have this button called the caret key, or it'll have this button, X to the Y power, or it'll have this button, Y to the X power. Whichever one your calculator has, use that and then type in 3. Now, some calculators will just spit out the answer. Others will just wait for you to hit the equals. But either way, you either got to hit the equals or wait for the answer, and we're going to write the answer right here. So when I do that with my calculator, I do 14.5, and I raise it to the third power, and I hit enter. I get 3048.625. 3048.625. That's what I got after doing that. Y'all should all be able to do that as well. Now what you realize is that's a cubed. So that's got to be equal to t squared. So I say this is equal to t squared. Well, if that's equal to t squared, I got to solve for t. What's the opposite of squaring a number?
Square root.
Yes, for those that are mathematically savvy, you can say this is square root. The other thing you can think of is you can say, well, if I raise something to the 2 power, the opposite is raising it to the 1/2 power. Or if I raise something to the 3rd power, the opposite is raising it to the 1/3 power. That's the way I'm going to teach you with this, because that allows me to just teach you this one button. Okay. So now what I'm going to do is I'm going to take that number that it gave me. I'm not even going to retype it back in because it's already in my calculator. I'm just going to go now with that button I have, and I'll type in 1/2, which is 0.5. And again, I may or may not have to hit equals depending on my calculator. And when I do that, I get 55.21436. And that is, remember, you were calculating the period, so that's years. Here's the problem. When I give you a problem like this, it'll be multiple choice. And I'll have 55.2, or I might just have plain 55. Answer A will be 55 astronomical units. Answer B will be 55 years. Answer C will be maybe me cubing this or squaring this first and then taking the cube root. So I make the common mistakes, the actual answers. So you got to pay close attention to what you're doing. Just because you see a number 55.2 that you recognize, that's not necessarily the right one. For instance, if it says AU, you're going to ignore it. But if it says years, then you got it right. So that's how you do that. Now let's try the other way. And this is the other type of math problem you're going to have to do. It's still the same one. It's just solving for the other variable. So now let's say I've discovered a new planet whose period of orbit in years is 0.21 years. I would like to know this new planet, Jabubala 2. I would like to know its astronomical units. I would like to know what its average distance from the sun is. So I'm going to say A is equal to question mark. So all I have to do for this is I've got to realize I've got t, and Kepler's third law says I need to square t. So I'm going to type in, notice I'm not using all the decimal places. I'm doing that on purpose. It'll give you a slightly different result. So I'm going to type in 55.21, and then I'm going to use my special key. Again, it's one of these three. Whichever one your calculator has, you're going to use it. And then I'm going to push 2, because that would make it square. Again, I may or may not have to hit equals. And when I do that, 55.21 raised to the 2 power, I get 3048.144. Okay. Now I'm just going to take that button, take that number, and I'm going to use that same button. And this time I'm going to put it to the 0.3333. Do at least as many digits as you were given. So I was given 4 here. I would do 5, at least 5, maybe 6. Okay. So now I'm going to take that number. I'm going to raise it to the 0.33333. That's 5 digits. So that's higher than the precision I was given. I'll go ahead and do 6 just for the heck of it. And now I had equals again. Again, that's a question mark as to whether you hit equals. That all depends on the calculator. In this case, I got 14.4992. And that's astronomical units. Okay. So that's how you use your calculator in the case of being given an astronomical unit and wanting to find the period. And this is the way you do it in the case of being given a period and asked to find the astronomical units. Notice it did come very close, 14.4992. So if I rounded it to 2 decimal places, which is what I was given it as, then it would have actually given me, since the 9's after that, I have to round that to 14.50. So that's consistent with it being the same planet. And they could be 2 planets at opposite ends of the orbit. They couldn't be in exactly the same orbit, and one would be, you know, half of this 55.2 year period ahead of them. Anybody have any questions on that? Okay, so when he did this, it became immediately obvious that this was a far superior model. It was easier to work with than the Ptolemaic model. It fit the data, including Brahe's data, the best ever. And again, the Catholic Church had no major problem with it. They just thought, again, hey, this is a really good idea. This makes the calculations a lot easier. It's not necessarily the way the universe is, but it doesn't matter. As long as this works, it works. So they paid no attention to it. Then comes this brash guy by the name of Copernicus, and you can look up numerous pictures of him. You can also see Brahe in here. The interesting thing, I got ready to tell you this, and I completely forgot. Brahe has this special characteristic. Remember, I told you he thought he was a good mathematician. He thought he was a great mathematician, but he wasn't quite as good as he thought he was. Well, what I meant by that is he got in a fight in college with a guy over who was the better mathematician, and he decided to have a sword fight, and he lost his nose. So Brahe literally lost his nose in a sword fight, and he wore a gold and silver prosthetic nose that he stuck on his face with wax. So that's Brahe. This is Kepler. So remember, he's like the Mike Pence, and then Brahe's like the Russell Brand guy. So it doesn't look like that from these pictures, but that's sort of what you need to imagine as their characteristic personalities when you're thinking about these people in history. Copernicus was, again, he was a person of the church, as was Kepler, and that's Copernicus. He was from Poland. All these guys are working across many nations, getting all this stuff right by communicating via letters and publishing books and stuff of that sort. All of that came together and led ultimately to a new way of thinking. Copernicus comes on, Galileo comes on the scene and wants everybody to recognize that not only is this a great model, that Kepler's laws of motion are fact. And he had read of a guy by the name Hans Lippershey. He had read of him creating a telescope, so he made his own, and that was what gave him the data to refute all but the Brahe model. And we'll talk about that next time. We are done. The class was over at 12:15. It just turned 12:16. Does anyone have any questions on any of this? Again, I will wait for the last person to leave before I leave. So if anyone has any questions, they're welcome to ask it. Remember also, we already had our lab. I've put up the original lab 1 that I couldn't find last time. That's up there, but you'll see there's not really any work there other than what I already told you to do, but you got a place to turn in both of those labs now. So look at week 1, week 2, and week 3, and you'll find what you got to turn in and where you got to turn it in. So you folks have a nice weekend. I will see you Monday.
Thank you.
You're welcome. Anyone?
No,
Hey.
no questions, none whatsoever.
That's cool.
I hated doing this the first time. God.
But you're so much more skilled now because you're in pre-calc.
Oh, to give me a break. I'm still putting things backwards. Now I'm dealing with SOHCAHTOA, and I'm just like, oh, so now you want me to put things backwards.
Yep, just remember cube and then square root, or square and then cube root. That's all you got to do. And since you probably have a nicer calculator, you don't have to just stick to that one button. You probably have a cube root button, so that'll be nice.
Yeah, I do have I have both. I have the square. I have one I can insert what I want, and
Right.
it's just
Some of these new ones, like I'm using this TI Inspire CX, which is like 160, 170 bucks or something. But they've taken the most useful buttons and put them in like menus. So if I want a trig function, I have to hit the button that says trig, and then I got to scoot over left or right to get sine, cosine, tangent,
Yeah.
cotangent, tangent inverse, inverse sine, inverse cosine. All of those are all under one button. It's just a nightmare. And if your finger is just a little bit fat, it's going to, knock you
Hit
off the right
everything.
one once
Yeah.
you get there.
Yeah, no, I just got your camera. It's horrible.
Yeah, that's why I take pictures of this crap. It
Yeah,
doesn't
I'm
turn out
glad you're
too
going to
good,
take a
does it?
picture of it.
Yeah, it's what's bad is I didn't do anything to try to make this look nice this time. So the picture is going to be of an ugly series of drawings. I think I did 2 pages though, didn't I? Yeah, I did.
Yeah, you did. Will you be doing open notebook like you did last term at any point?
The online test will be, but not the midterm.
Not the midterm. Yeah, well, you didn't do the midterm last time.
Yeah. Ideally, what I would like to do, but I'm not allowed to, is I'd rather just make people go to the testing center and take the midterm and the final. So I do Respondus instead. But that sort of knocks out the idea of much cheating. The online test, there's not cheating. And so you get exactly, what you expect, which is a student having a limited amount of time, but still enough time to look up stuff. So I don't mind that. And I made that fraction of the grade a fairly small fraction for that reason.
You do know there are ways around Respondus, right?
Yes, I know there's ways, but at that point, if you're
you're
that
that
diligent, you're
desperate.
probably going to get it. Yeah.
if you're that desperate, maybe you deserve an A for cheating.
No, it's more like if you're good enough and savvy enough to put that work and ethic ethos into actually cheating that way,
Yeah.
then you're probably bright enough to have done well in the class, and you're just screwing yourself. So
Yeah, pretty much at that point. Just
yeah, it's
oh
just
my god.
we were briefed on, I think it was Blackboard when we had that, and they told us this does this and it randomly generates this, and if your students are capable of hacking this, then they deserve an A in their class anyways. So I was like, yeah, I kind of agree with you on that.
Yeah, they use your camera to watch your eye motion.
Yeah. Yeah, and that's actually what Respondus does. And not only that, I got a ton of warnings last time. It was like person acting odd, and what I looked in on it, and the person kept getting up and turning off the something on the speaker that Respondus was putting out, saying, "I can't see your face. I can't see your face."
Yeah.
So I looked at it and like, okay, well, that's no big deal. So yeah, Respondus with the monitor is actually pretty good. And the reason I know it's good is because my test averages go from 90s to 60s.
Yeah. Yeah.
So not too many people are gaming it.
It's hard to game that system.
Yeah. So anywho, you got any big plans for this weekend?
Staying home, staying away from COVID.
Yeah. Actually, I just looked up a map in the New York Times, and all but like 6 counties in North Carolina, and they're, one of them's Goldsboro, and the other one's like near Raleigh. All of those counties are at extremely high risk.
Oh yeah, yeah.
And the 6 counties that aren't, they're at very high risk for it right now.
Yep. It's stupid. It's stupidly insane.